Hello, everyone. It's time to start my session. Hope everyone is having a great CVPR so far. I'm certainly enjoying it, attending CVPR from my bedroom, as you can see. It's 6 a.m. here in Adelaide. Okay, so my title is Mathematical Programming Approaches in our tutorial. So mainly in this talk, we'll be supported by a lot of my fellow colleagues, thanks to them. But mainly it's myself and my student Zhipeng. As you can see, I've named him my wingman. And he's called a wingman for at least two reasons. Number one, you see those two big cockatoos on his shoulders. The second reason I call him a wingman is that he'll be collating your questions if you type them in a chat window and interrupt me and ask the questions on your behalf if necessary. If I don't look at the chat window in real time. Okay, speaking of cockatoos, it's actually an actual thing in Australia. Tourists get attacked by cockatoos. So Zhipeng's photograph in the previous page is totally legit. Anyway, if you're not familiar with Zoom yet, at the bottom of the window, there is a chat functionality. So I prefer that if you have any questions that you don't want to ask through the voice channel, please type it in the Zoom chat window. We understand that there's another forum on the CVPR virtual. I don't think that we're monitoring that that closely. Maybe Daniel is, but I prefer if you could type in a chat window so that we will be able to monitor it more closely. Zhipeng, if you're there, can you say something so that everyone can hear your voice? Can you unmute yourself and say something?
Hello. Hey guys, can you hear me?
Yes,
Hello,
we
TJ.
can hear you. Thank you, Zhipeng. So maybe leave your video on as well so that we all know you're still there.
Okay.
Awesome. Okay, so I've been allocated 1.5 hours for this talk. We may have a short break. I emphasize may because I may not have enough time to cover everything. But this is Zoom and this is CVPR. You can move around tutorials as you like. But of course, I hope that you stay for mine for the whole duration. Okay, so here's a brief outline of what I'm going to touch upon. Number one, I'll give you the bad news. You might have heard of me talking about this bad news before regarding what is and isn't fundamentally achievable for robust fitting in general and RANSAC type algorithms in particular. Then we move into global algorithms and deterministic outlier removal methods, as well as deterministic refinement methods. We'll talk about some experimental results. Now, in Professor Irji Matas's talk earlier, you've seen him talk about RANSAC in 1755. The title of our tutorial overall is RANSAC in 2020. The final segment of my talk, I hope to bring you to RANSAC in 2040, where we start to talk about quantum approaches for doing RANSAC, at least the early stages of doing that. So this is hot off the press, some recent work that we're doing. Okay, so let's start with the first section. Okay, so in order for us to do analysis, we have to simplify the problem. There's just a whole zoo of different instances of robust fitting, so many kinds of objective functions, so many kinds of models to fit. You can't have an analysis that, not that you can't, it's difficult for a non-expert like me and for most people in computer vision to analyze if we don't simplify. So the particular simplification we look at is the simplest possible fitting problem. Given measurements A and B fit the linear relation AX minus AX plus B. Okay, so in doing so, we are identifying a special variable B where we say that, this is where all the errors lie. Okay, and effectively the residual considers only the error in B, and we expect that error is within epsilon if it's an inlier. Okay, and then the usual inlier counting objective function says find me the model X that has the most number of inliers. Okay, we're all familiar with this. Again, to emphasize, most vision problems do not have this kind of formulation. Some of us convert our favorite problems, homography fitting, essential matrix fitting, into this form. That's always possible. But usually we don't do that. I'm doing that here, not because I'm saying it's practical. I'm doing that here because I need to simplify it to do my analysis. Okay, so this is an instance, the simplest instance of that simple version, which is a 1D problem. X is only 1D, and A is here, and B is here. And the problem reduces to finding a line that passes through the origin where there are as many inliers as possible, okay? And the residual is, in fact, geometrically this straight line here, vertical line that connects the point to the model. Okay, so this would be a model with a low consensus because it isn't a low number of inliers, a consensus because it doesn't have a lot of inliers. This would be a model with a high consensus, just to check that we're on the same page. Okay, so how would RANSAC work? RANSAC, as we all know, would sample minimal subsets. In this case, we only just need 1 point to estimate the model parameter x, a scalar, and therefore, in this particular instance, you would sample single points, fit that line through the point. Remember that line has to pass through the origin. That's why 1 point is sufficient. Okay, and then we use the same rule to check which is how many inliers a model has, and also we use this formula here to determine how many samples we need to draw, okay? So that we get at least one minimal subset that contains only inliers. Okay, so far so good. In fact, for most real life instances, if indeed you have one-dimensional linear problem like this, yeah, RANSAC would work. But here is an adversarial case for RANSAC. It's contrived, totally understand that. But again, we're trying to analyze the fundamental nature of the problem. So contrived instances are useful for that. What can you say about this line? I forgot to say that I like to ask questions during my talks and lectures. What can you say about the maximum consensus line that you want? Can anyone in the audience, do you dare to say anything? Anyone want to jump in and answer the question? What can you say about the line of best fit with the most number of inliers? Anyone?
It seems bad.
Why is it bad? It has a lot of inliers.
If you choose epsilon smaller than the one that you use, it will have no inliers.
Oh, that's true. But let's say, thank you for that. Maybe my example isn't great, but let's say I put other points here that are outliers. Okay, I put 4 outliers in there. And then let's say epsilon is correct for some reason. Then according to our objective function, this is the best line. Okay, it has the most number of inliers. Evgeny, you probably said that it looks bad. I agree with that. That's probably the contrived nature of this problem instance. What else can you say about the line? Let's assume that this is good enough, but what else can you say about the line based on what we said in the previous page? Nick?
The way you're fitting it, where you're randomly selecting a point and connecting it to the origin, you could never generate this line.
Perfect. Thank you for that. Because the line that we want, the optimal line, does not pass through a point. Okay, it doesn't pass through a point, but if you use RANSAC, all the line that it's able to generate or it tests, even if you test all of the candidates, they have to pass through a point. Okay, but the optimal line here does not pass through a point. Indeed, if you consider only lines that pass through points, they will never get the maximum consensus set. Okay, that's a fundamental fact. It is contrived, yes, but as I said, this is to illustrate fundamental problems, limitations of methods like RANSAC. Not saying it's not practical, not saying you can't build a self-driving car using RANSAC. Yes, you can. I'm just being my fussy, usual self. What you can and cannot do, this is what you cannot Okay, so that brings us to this topic of fundamental limitations, right? I'm not going to spend a lot of time on this, and we already covered this in previous tutorials. Might still do it in future tutorials. Sorry if you see me again talking about this. So we've published in 2018 some results that says, hey, this problem of maximizing number of inliers is NP hard. You can't solve it in polynomial time. And we also show that it's W1 hard in the dimension. Practically what that means is, without going into the details what W1 hardness means, it means that any algorithm that we design to solve it globally optimally, the dimensionality of the problem has to appear in the exponent of the number of points that you have, okay? You can't go any faster than that. The fastest you can go is n to the d. That's fine, but that's still considered exponential because d is part of the input dimension, okay? This is the fastest you can go. We also show that it's APX hard, and what that means, again, without going into the details of what the APX or the approximable classes of algorithms are, APX hard just means that there are no polynomial time approximation algorithms. And by approximation algorithms, we mean algorithms that can give you an error bound when they finish. Okay, if you use RANSAC, if you're experienced in RANSAC, you know that it doesn't give you anything. All right, it spits something out at the end and it says, this is it. I don't know how far it is away from the optimum, and that's it. Take it or leave it, right? Again, not saying that RANSAC is not practical. Tremendous amounts of progress has been made. Totally acknowledge that. But again, being my usual fussy self. Okay, so there are other negative results as well. For example, by my colleague Luca and his team at MIT, minimally trimmed squares is kind of also a popular robust fitting criterion. And they show that there are no quasi-polynomial time algorithms to solve this problem as well within any factor lambda. Okay, so similar with our APX hard result in the previous page. Okay, so you might say, yeah, big deal, but there's a host of other robust criteria that we can apply. Okay, so we can generalize the ones we've seen before, count number of inliers or minimally trimmed squares. And in fact, you can even invent your own, no issues with that. And we therefore go into the topic of M estimators, whereby we look at generic robust loss functions and the ones that's, okay, so for example, Tukey's byweight is one that, that's quite popular. And you can see that it has this, this non-convex shape as well, so that influences from outliers are ignored. If we put our inline accounting objective function in the context of M estimators, it would look like that. So inliers would be penalized with the same amount. It doesn't matter how far they're away from your model. If it's far away enough, in this case, the inlier threshold is one unit of your residual, then it's no longer, then its distance no longer matters, okay? Similarly, for inliers, if you're within this region, we count you as one. We don't care how far you're away. Okay, so there are other robust criteria possible. We'll look at Tukey's byweight. Given McClure is another one. There are probably many others, but the ones that are truly robust, those that can really ignore lots of amounts of outliers in a hand-wavy way without giving you fundamental characterizations in terms of breakdown points, the ones that really work well are the hard redescenders, and they tend to be non-convex. And if they're non-convex, that means that you bump into the same computational hardness results as before, maybe not the exact ones. And what I say shouldn't be surprising as well. If the problem is non-convex, it's not solvable globally in polynomial time. That's it. That's all we're saying. Nothing surprising there. Okay. Then I hear some of you cry in exasperation. Sorry for harping on this point again. Some of you might say, hey, but RANSAC works well. Why do I care about results? That is totally fine. Nobody has to care, but here are a few points I want to make. RANSAC, when it works, it's not the problem. RANSAC and its variants, to be fair, when it works, it's not the problem. It's when they don't work. Okay. Often when it doesn't work, you don't know why it doesn't work. I mean, if it doesn't work, is it because it doesn't work, meaning it doesn't give you a model with a lot of inliers? When it doesn't give you a model with high inliers, high inlier count, you don't know if because there are no high inlier models in there or because you were unlucky. Okay, because the algorithm doesn't give you anything. It's fast, no doubt about it. So most practitioners would do what? If you're using RANSAC, if you run it one time, run it using the stopping criterion, the standard stopping criterion, it doesn't give you a good fit, what do you do? Again, pose it to the audience. What would you do?
Run it again.
Run it again, okay? So you run it until you get something you like, and then you stop when you're satisfied, okay? For many, many, many applications, that's probably fine. I'm okay with that. So by all means, continue to use RANSAC. Okay, so why does it behave like that? Well, Andra, my colleague, probably mentioned degeneracy as a possible problem, and I've also shown you adversarial cases. Even when there's no degeneracy, right? The fundamental assumption that the algorithm makes does not hold, which is that all it's trying to do is to find an all inlier minimal subset with the assumption that all inlier minimal subsets will give you a high consensus. Okay, I think Yirji mentioned this in his talk as well. So here you can see they're all inliers here. You know, if I just pick these two inliers, you can see that it doesn't give you a high consensus model. All right, and not all inlier minimal subsets give you good fit. Again, sorry for harping on this. Why should we care about theoretical hardness? I think it's useful for let's say, you know, theoreticians. It's also useful for practitioners to know about fundamental limitations. Okay, if we know about the fundamental limitations, we know about how algorithms can be classified into groups. Kind of like how we go into a jungle and classifying species of animals in there. We want to do the same with algorithms as well, and that's what, you know, theoretical computer scientists do. I think we in computer vision, algorithm designers in computer vision should do more of that as well. We want to, if we're able to classify, we're able to group algorithms together according to their similarities, we can predict their performance. Okay, many of us will review papers, a lot of papers in a lifetime, and, you know, for example, an author claims that an algorithm can do this. You know, if we have that understanding of fundamental limitations, we know already whether that's probable or not. Okay, we probably don't have to look at the table with bold numbers in the experiment sections to tell us whether this algorithm makes sense or not. From a more proactive standpoint, if we can predict performance, then we can also design our algorithms better. You know, what aspect of our algorithms should we test? In the context of robust fitting, should we just vary the outlier rate or inlier noise, which is usual? Or should we vary the number of outliers, right? Number of outliers, not necessarily the same as outlier rate. Should we vary the dimensionality of a problem? Or should we just focus on that specific problem we want to solve? For example, let's say a homography fitting, and ignore how the algorithm would work if we transplant it to a point cloud registration problem. Should we consider distribution of inliers, distribution of outliers, etc., etc.? Okay, so if we know fundamental limitations, it also helps us to focus on where we should devote our efforts, right? Maybe, you know, because the limitations are so severe, maybe the bad news from TJ is so bad. By the way, everyone calls me TJ, right? Maybe the fundamental limitations that TJ says are so bad, we shouldn't publish any more papers on this. I know it's sacrilege, you know, CVPR culture, but, you know, maybe that's what we should be saying. maybe we should ask, what's a better way of moving forward? Perhaps deep learning is a way to go. But then there's increasing evidence that they don't generalize well. Then should we care about the tables with bow numbers? If I want to use this method, I have to retrain it and collecting 50 gigabytes of data before it can work. Is that a system that works well? Maybe it is for some applications. Absolutely, don't deny that. Maybe it isn't. Okay, sorry. Okay, so back to the fundamental limitations. Hopefully now all the bad news are finished from my part. What does the theory allow us to do? So on the left-hand side, we have heuristic algorithms, usually randomized in nature. On the right-hand side, we have the globally optimal algorithms, okay? So the left-hand side ones are usually really fast, okay? The right-hand side one, the theory says it has to be slow, okay? It has to be slow, unless P equals to NP, all right? It has to be slow. And who knows, maybe one of us CVPR researchers will crack P equals to NP against the conventional wisdom. On the left-hand side, the theory says if you want fast, you cannot have guarantees, okay? At least not direct guarantees in the original formulation of the problem. There are other kinds of guarantees. On the right-hand side, if you want optimality guarantees or even an error bound, you can't have polynomial time. That's what it's saying. On the left-hand side, so far, a lot of the heuristic or approximate algorithms are random in behavior. On the other side, it's deterministic. Not really. Maybe there are randomized globally optimal algorithms as well. So maybe I have to take this back. Okay. So then, what's in the middle here? What can we do? What can we look into for future research? Any suggestions? My suggestion is, at least we can fix, we all want fast, okay? We want our self-driving cars to work. If we want fast, we know that we can't get any guarantees, okay? That's a fact that we have to live with. Maybe at least we can fix the random behavior, okay? Sorry, I don't have your name, but one of you replied earlier that when RANSAC doesn't give you a good result, you suspect that, maybe I was unlucky because it's randomized. I have to run it again, all right? At least maybe we can fix that part, all right? Make it deterministic, all right? So that's the next, okay, that's not the next one, the two next one. The next two after the global algorithms, make it deterministic, but still approximate. But first, we go through a preview of global algorithms. I'm not going to spend a lot of time to talk about the details of the global algorithms. I'm really just going to whiz past. There's a lot of them to cover. I'm not going to cover them before in other tutorials. So one big class of global algorithms would be branch and bound. That's a standard toolkit in a global optimization textbook. How it works is it recursively tests and prunes the search space. Okay. So if this is your search space and this is your objective function, highly non-convex, you would cut it first, and then you would bound it. You bound it meaning if my objective is to maximize, I find a number that is definitely higher than the highest possible value in that region. Similarly for that region as well. Okay, and then I compare the bound with the best value I have so far, and that enables me to, let's say, if this is the best value I've found so far, then I know that my answer for the global optimum will not lie here, and I'm going to throw it away. All right, so that's a very quick explanation of branch and bound. In computer vision research, mostly our problems are here. For that particular problem that you're looking at, to use branch and bound, how to parameterize and subdivide the search domain. All right, in this simplified example here, it's a 1D line. The search domain is a 1D line. We have parameterized it. Subdividing is easy, can chop it up into segments. This question, parameterization and subdividing, is not necessarily easy for the computer vision problem you're looking at. and then how to bound the objective value, okay? So these are the two questions that require work, but once you sort out these two, the general machinery of branch and bound works, and you should be fine. Okay, so this will guarantee global optimum, branch and bound, but the theory says it cannot have any sub-exponential bound in general. Maybe there are special cases where the branch and bound will, maybe there are special cases of problems in computer vision where you can get a sub-exponential bound. That will be fantastic. But in general, there is no such bound, sub-exponential bound. So in computer vision, we have applied branch and bound for robust fitting for many applications. You can see them on the left-hand side there. 3DOF and 6DOF registration problems with correspondences and without correspondences, epipolar geometry estimation, PNP, LiDAR, camera registration, conformal registration. We'll talk about two of them later as a quick preview. Now, branch and bound does not necessarily apply to consensus maximization only. There have been a lot of other robust criteria. And such algorithms tend to be more bespoke, tend to be more customized for the particular problem, because, you know, the parameterization and the bounding function changes from case to case, okay? The overall algorithm is similar. How you chop the space up, how you prune, how you bound, how you prune, that's generic. Yeah, but then after that, anything deeper, lower than that level is customized. It's typically slower than global algorithms, but speeding up requires creativity. And for me, I think that's interesting because that's a problem I can't just dump data on GPU to solve. And in my opinion, this is still a fruitful research direction. So here are two, exotic cases that we've looked into. On the left-hand side, conformal registration of 3D surfaces. The model that we're looking at is a bit different than the usual homography or affine transformation that we look at in computer vision. So it requires a lot of understanding of the mathematical model and how to bound the objective function based on the model. On the right-hand side is more recent work. We're going to have my student, Dachi Liu, is going to have a paper in this conference on using branch and bound for contrast maximization. And CM, or contrast maximization, is used extensively in event-based motion estimation. So some of us know that event data looks like this, where you have an X, Y dimension and a time dimension. And, because the event camera does not detect intensity, but intensity changes. So as the camera moves around the scene, there are intensity changes on the optical plane, and it generates an event stream like that, okay? For us to uncover the structure of the scene and to estimate the motion that the camera experiences in the process, we have to do some optimization. Without optimization, if we just collapse the time domain, we see that kind of a blurry scene. And contrast maximization is an objective function to recover that sharp scene structure. We do it with a local algorithm, you get the result here. We do it with a global algorithm, which is our algorithm, we get a much sharper result. So check out Daji's paper if you're interested later. Okay, so another class of algorithms, global algorithms for robust fitting or consensus maximization in particular are basis search methods or subset search methods. One particular method under this class checks all the bases of the problems, okay? Sorry, I don't have a lot of time to go into what basis means. In fact, actually we'll touch upon a little of that later. Effectively, a basis is a subset of the data of a known size, usually not that much larger than the dimensionality of the problem. And you can prove that the solution you're looking for must lie in one of these bases. So therefore, one solution for the global algorithm is to check all these bases, enumerate all of them to find the one you're looking for. And previously, we looked at, hey, we understand actually that those bases can be arranged in a tree structure. where the levels of the tree tell you, that consensus solution corresponding to the basis, the level of that basis in the tree is the number of outliers of that consensus set. Okay, so therefore we can search the basis layer by layer, and that enables a positive result in consensus maximization, which is that it's fixed parameter tractable in the number of outliers and dimension. So the algorithm that we propose is exponential only in the dimension, as before, but then the base of the exponential is the number of outliers, not n. Okay, the polynomial factor, we don't have to worry about it, it's polynomial anyway. But compare this to the previous W1 hard result. If you know nothing but the dimensionality of the problem and the number of points you have, you can't go faster than n to the d. That's what W1 hardness says. In our algorithm, if you additionally know, hey, I don't have a lot of outliers, outlier count, not outlier rate. If I don't have a lot of outliers in my problem, I can have an algorithm that runs in O plus 1 to the d plus 1. Okay, so if O is much smaller than n, this algorithm will be much faster than the one that runs at n to the d. Okay, so here's another avenue that I personally think is great for research. We know global algorithms cannot be fast. The theory already rules it out. But the theory doesn't rule out algorithms where if we provide additional knowledge about the problem, we can maybe come up with algorithms that are faster, that are globally optimal. Okay, faster meaning that you can bound it with a tighter bound on the runtime. Okay, what additional structures about the problem? Okay, so one is the number of outliers, which we discovered. Maybe there are others. Okay, to be honest, I haven't, I'm doing a do as I say, not do as I do thing here. To be honest, we haven't found other problem structure ourselves, but my team is small. That's my excuse. Maybe there are other problem structures that we can exploit to speed up the problem. That would be a really cool thing to do. Okay, another class of algorithms that I put under global are preprocessing methods. Okay, so before we go into what preprocessing methods are, here's another viewpoint of what suboptimal algorithms like RANSAC does. So we have, let's say D is the overall set of data points we have. And amongst these sets, the green sub-areas, the green subsets, are the consensus sets. Okay, so these are sets of points where they can form a consensus set. Okay, all the points in the green area can form, let's say, a line where all the points lie within an epsilon that you set from the line. Okay. The problem of consensus maximization is to find that biggest subset, that biggest consensus set. And suboptimal algorithms, proximate algorithms, may find a subset like that, for example. Preprocessing methods do not try to find I or I star, do not try to find I tilde or I star. It tries to find D prime, okay? Where D prime is a set that's smaller than D, and D prime must contain I star. Again, D prime is smaller than D, as you can see here. D prime is smaller than D, and D prime must contain I star. Okay, I call that preprocessing. I call preprocessing because it doesn't really solve the problem you want. It just reduces the size of the data to a kernel. I don't like to use this word in front of ML people and CV people. It means different things. But in the theoretical computer science literature, it is called a kernel. Reduce D to a kernel D prime, where the optimal solution still remains. Okay, so practically what would it look like? It looks like this. This is one preprocessing algorithms that I personally believe is quite successful. You have you know, let's say in a 3D registration problem, we have 2,000 correspondences, 98% outliers. We're able to come up with an algorithm that does not find the maximum consensus set, but it's able to find a D prime, a kernel, in 4.62 seconds in this particular problem instance, where there are only 60 correspondences left and 28% outliers. And the algorithm guarantees that the inliers in the original set does not get removed. Okay, so what's the benefit of getting this? Well, number one, you see that the outlier rate has been significantly reduced. Number two, you see that we only have 60 points to deal with. Okay, when your algorithm runs in n to the d, getting n down from 2,000 to 60 is a big deal. Not going to go into the detail of the algorithm. I'd like to jump from this to the, after this, to the deterministic approximate method. So another class of global algorithms you can look at, which are certifiably optimal relaxation problems. These are algorithms, roughly speaking, not doing justice to this very interesting class of methods. You make your original problem simpler by relaxing it, and then you set it up so that you can check that after you solve the relaxed problem, you can still sometimes achieve strong duality, meaning that when strong duality happens, your solution to the relaxed problem, you can guarantee that it's the same as the solution you would get, global algorithm that we get, global solution that we get if you did not relax. Okay, another fruitful avenue for research, in my opinion. Okay, so this is an example I want to use to show that global algorithms are not just theoretical novelty. Okay, so this is a method. I'll just jump straight into it. Hope it works. So MapTech is a company based in Adelaide, not far from where I work, and they build laser scanners. They also build an awesome software package that comes with the laser scanners. And, you know, being in Australia, we're heavy on the mining industry, and therefore MapTech is primarily targeting the mining industry. And we help them build a point cloud registration algorithm that looks like this. So this is a part when it starts to do global registration, globally optimal registration. Not real time, you know, the car is not moving and then scanning and registering at the same time. But for this particular application, after the surveyor has scanned the different pieces, he or she wants to put back those pieces together. Our global algorithms allows this to be done fully automatically. The user just needs to press a button, go get a coffee, and then come back, and the result is done. Compare this with the previous workflow that they had in this software. They use ICP, which means that the surveyor has to sit down and carefully, you know, align the two pieces roughly already, and then hit the ICP to refine it. With our global algorithm, that is not necessary. So you can see the global algorithm happening as we speak, as I speak. There's another example at the end, I think. So that's a finished result, but I think they'll show after this how it works. Yeah, so that's when it's the global algorithm is working out each of. I think this is probably speeded up. Yeah, but you know, the company thinks that this is a sufficiently big enough improvement to their existing workflow that they incorporated our algorithm in here. So yes, global algorithms can be practical. They can have commercial. They do have commercial value. All right, so I think I'm doing good in terms of time. Do we all need a rest? Have you been given breaks, or are you happy to move forward? I think let's just move forward. if there's any objection to that, let me know in the chat window. Zhipeng, any questions in the chat window so far?
Not yet.
Okay. If there's any question, just interrupt me, okay?
Okay.
Okay, so we look at 3 types of deterministic outlier removal methods. First type, L-infinity method. I think this is quite well known, proposed by Professor Hartley and his student. We look at a very different problem to the robust fitting. We look at, in fact, totally non-robust fitting to begin with, and that's what I call the Chebyshev problem. In fact, not that I called it, but in the statistics literature, it's called the Chebyshev problem, whereby if we're given the same kind of data, simple data that we discussed at the start, we want to find a model that minimizes the maximum of the error. Okay, so firstly, for this problem formulation, this is a linear program. So we know that this can be solved efficiently. So we don't have to go into that. In fact, we just set it up in let's say MATLAB and run linproc, and it's going to solve it for you. No problems. Okay. Geometrically, for any dimensional problem, in linear problems, we're trying to find a slab that we are trying to find a smaller slab that encloses all the points. Okay. So the size of the slab or the width of the slab is this vertical direction here. Okay. So if we solve this problem, it's going to find us this line. It's actually going to find us this line. And we know that this maximum distance is minimized. Okay. So that's the Chebyshev problem. In fact, if this is the same problem as if we stack all the residuals, residuals from all 10 endpoints into a vector and take the infinity norm of that vector, and the infinity norm of a vector basically gives you the largest element in that vector, hence the max here, then we are in fact, the Chebyshev problem is minimizing the L infinity norm of the residuals, okay? And this is of course still a linear program. We've just changed the notation of the problem, but at the heart, it's still the same linear program. That's why sometimes in this area in computer vision, it's called L infinity minimization. Okay, so here are a few fundamental facts about L infinity minimization. There will be active points whereby after you minimize, they are of the same distance to the line that you just found, and that distance is the minimized maximum distance. Okay, there will be such points. Okay, intuitively you can imagine if you're trying to find the slab that is as thin as possible that encloses all the points, you can make the slab smaller until it's going to hit points that you can't go further anymore. The points that you hit first are called the active points. Okay, so some of you might say, hey, why can't we make the slab that way? For this problem formulation, remember, we're considering the 1D problem, so all the lines must pass through the origin. I'll show you problems later where we don't have to pass through the origin. Okay, so there will be active points. In fact, we know the size of the active points. The number of active points has to be at most D+1. Hence, the idea is as follows for dealing with outliers. As I said at the start, the Chebyshev problem is totally non-robust. You can see here, there are outliers in this problem, and it has indeed biased the estimated X, okay? But what can you say about the active points? What you can say about the active points is that they tend to be outliers, all right? The intuitive idea is that they tend to be outliers. In fact, you can prove that one of them, at least one of them, must be a true outlier. I'm not going to go into that in this tutorial. If we know they tend to be outliers, then hey, why not just remove the active points and then solve the Chebyshev problem again, remove the active points and keep doing that until the error of the fit is within epsilon. Okay, so hence this is called an outlier removal problem. This is how it would work on a synthetic data of 2 dimensions. So now our line is not constrained to go through the origin. Our active set now is size d+1,3 because of increased dimensionality of problem. You have to estimate the offset of the line, not just the slope of the line. But it works the same way. We can guarantee that, you know, d+1 of the points at least will be active. We remove them and then solve it again, keep removing until we end up here. Okay, so that's the idea for L infinity removal. Here, okay, so we've looked at linear models. The nice thing about L infinity in computer vision problems is that it can handle quasi-convex problems well. What do we mean by quasi-convex problem? What is quasi-convex? A quasi-convex function is a function where every sub-level set of the function is convex. Okay, what do we mean by a sub-level set? The sub-level set defined by S of this function is if you threshold this function and you look for the subset of the domain of the function that is below the value S. Okay, for the function here, this would be the sub-level set for this value S. If I move this S up or down, I think all of you can imagine that the sub-level set here is always a contiguous line segment, which means that in the one-dimensional line, it's a convex set. Contrast this to a non-quasi-convex function here. Here I find an S, find a sub-level sets. There are 2 of them here. So these 2 areas are the sub-level sets. Taken together, they are non-convex sets. Okay, so therefore, the one on the right-hand side is not a quasi-convex function. I think I have an animation of this. Something went wrong. Okay, so you see here. Oh, I can't annotate here. Oh, sorry, hang on. Got kicked out. Oh, YouTube doesn't allow me to do this. Okay, sorry, can't do that. Blame YouTube. Okay, so sorry, I couldn't show you the animation, but I think I think all of you can imagine that if I move this up and down, this set is always contiguous and hence convex. And for this function, if I move this up further, if I move it up here, then the sub-level set is convex, okay? But not all S's will give you convex sub-level sets. Only the quasi-convex ones will, all right? Why did I spend so much time harping on this? Well, several or a number of computer vision problems involve residual functions that are quasi-convex, okay? I'll give you 2 examples here, triangulation and homography fitting, where for the triangulation, we use the reprojection error. For homography fitting, we use the transfer error, and these errors are quasi-convex. By the way, I think it's apparent, I hope it's apparent, that convex functions are also quasi-convex, because no matter where I put the S, the sub-level sets are still convex. Okay, so quasi-convex, as the name suggests, are almost convex. Okay, but they're not convex because they don't satisfy the definition of convexity. If I have 2 points here and draw a straight line, you can see that this straight line is below the function. Okay, so it's not convex, but it is quasi-convex. Cool. Okay, so then, you know, how does this help us in terms of robust fitting? Well, the maximum of a set of quasi-convex function is still quasi-convex. You can see that on the right-hand side here. I have a bunch of quasi-convex functions in blue. If I take the maximum of these functions, I get this red line at the top here. Okay, and it's easy to prove that the maximum of a set of quasi-convex functions is still quasi-convex. For the top function here, the red color one, it doesn't matter where I put the S, the sub-level set is always contiguous line segment in this case, and hence convex. All right, in general, it holds true. Now, the L infinity formulation or the Chebyshev formulation for the quasi-convex is minimized over the maximum of all these residual functions. And the quasi-convex nature of that maximum function allows us to solve this problem efficiently. And there are many methods to do it. You can use bisection with convex feasibility test. You can use SQP. You can use generalized simplex methods. You know, the point is it's easily solvable. Not going to go into the specifics, but it's easily solvable. You can also see an inkling here of the notion of the basis. If you look at this maximum function here again, if I ask you to find the minimum point, for us humans in a 1D problem, it's easy. It's there. There's a minimum point. Okay? You can see that the minimum point is made up of, is at the equilibrium point of exactly 2 of those quasi-convex functions. Okay? So, you know, there's therefore also the basis concept that we mentioned earlier. And that allows us to do outlier removal as before. This is a circle fitting problem. We're trying to find the smallest circle that encloses all the points. And you can prove as before that you make the circle as small as possible. Eventually, it's going to touch a number of points. And you know that the number of points is d plus 1, which is 3 in this case, because our d is, what is our d? Our d is actually 2, the center of the circle. We're trying to make the radius of the circle as small as possible. Therefore, potentially we can hit 3 points, but don't worry about the d. If we solve the Chebyshev formulation for this problem, we're going to hit active sets like that. We remove the active sets, keep fitting the rest of the points until we find the size of the circle that is less than equal epsilon. Okay? Same as the maximum consensus formulation. And you can see here the traces of the circles that we have to continuously shrink in order to find that epsilon circle. And that epsilon circle that you find is not guaranteed to give you the one that covers most of the points. That's the pink one. The black one is is one that we eventually found using this outlier removal routine. So it's suboptimal. Of course it's suboptimal, right? Because as you know, the theory already tells you that. So this is a synthetic triangulation problem. So in triangulation, the measurements are actually these point-wise measurements of that 3D point X. Okay, we're trying to find the 3D point where the reprojection errors to the cameras are within, where the reprojection to as many cameras as possible are within epsilon. Okay, so we can use a min-max formulation for this. As we mentioned earlier, it's quasi-convex. You solve the min-max problem, and you get a 3D point here where it's reprojection, maximum reprojection error to all the cameras, 0.4819 pixels. We remove the points that are active. These are the active points. We remove them and keep solving. So this is the next iterate here. That's the active point, active data points, remove them. These are the active ones again. You see that the estimate has changed until we get to a situation where the min-max value is within epsilon. Okay, so far so good, seems to work. It's number 1, as I promised at the start, it's deterministic. There's no randomness involved, all right? additionally, actually, you know, as I said earlier, I didn't want to go into detail, but you can say something about the points that you remove as well. You can guarantee that at least one of them is a true outlier, but let's not worry about that. The problem with this approach is when the data is unbalanced. You can see here, when the true structure is not in the middle of the distribution of the points, you end up removing too many of the inliers before you converge. And then your result could be heavily biased. So yeah, deterministic, but you know, it has this pathological problem. Let's next look at the L1 problem. Okay, so let's go back to the Chebyshev again. We were just seeing this. Instead of minimizing the maximum residual, this is a completely equivalent formulation. We introduce a slack variable S, and we want to make S as small as possible, but we want to make all the residuals to be smaller than equal to S. Okay, exactly same as before, just introduce an additional slack, that's all. All right, also still a linear program. In the L1 version of it, instead of minimizing one S, we introduce a slack for every point. Okay, every point now gets its own slack. We want to minimize the sum of the slacks. By the way, do I need to add this constraint? All the S are non-negative? Anyone? Do I need to add the constraint that the slacks are non-negative? Is this required? You can type in the chat window. It's not required because this quantity is always positive. Okay? The constraint says S must be greater than an always positive number. So this constraint is unnecessary. Anyway, the L1 method sums the slack instead of finding only the maximum one. And you know, the sum of the slack is the L1 norm of the vector of the slacks. That's why I call this the L1 method. Additionally, in computer vision, we added additional threshold here to implement the understanding that our models are never perfectly fitting the data. It's only accurate up to some epsilon. Okay, so you know, but you know, it's still a linear program. It's still the L1 method, as I call it. And the method works by, you know, as before, solve the problem, remove the points with positive slacks. That's it. If a point has a 0 slack, that means that point is within the epsilon. So that's considered an inlier. Okay, so far so good. So for example, with a you know, problem instance like that, it works quite well. You can see that these are the points that are outliers. And if you have points distribution like that, it's hard to predict what's going to happen, but you can see that even in this simple problem, it's easy to bias result. So again, you know, it's not great, but it is deterministic. So next version, it would be what we call the K-slack method. That will be the middle point between, as you'll see later, the L infinity and the L1. Instead of minimizing the maximum one or minimizing the sum of all of them, let's minimizing the maximum of the K of them. Okay, so pi here, by multiplying with S, dot product it with S, we are allowing, by forcing this pi dot product 1, vector 1 to be K, we're forcing to sum only K of them. And if we are maximizing the sum, we're finding the K largest residual to sum over. Okay, that's what it's saying. If we set K equals to 1, if we set this to 1, then this goes back to the Chebyshev problem. If we set K equals to N, then we're summing all of them, it goes to the L1. Okay, so K is an additional parameter that allows us to control how many of them we want to pay attention to. And this also has an equivalent linear programming formulation. And if it's quasi-convex residual we're talking about, again, we can solve it efficiently, no issues there. It allows, so this method allows us an additional parameter to control how aggressively we want to prune the points, okay? But it works the same way. Solve it, check the points whose slacks are above 0, remove them, and solve it, keep solving it recursively until we get to a model where none of the points have positive slacks. Okay, so here are some results to show you the effects of varying k. The left-hand side is the least aggressive, but at every iteration you remove only d+1. And the right-hand side is very aggressive. You might end up removing more than you need. If you set an appropriate k, it allows you control. I can be faster than just removing d+1 points every time, but then, you know, maybe I don't go as aggressive as the one on the right-hand side. I still retain some of the inliers. Okay, so I think, yeah, we're doing okay in terms of time. A bit slow for my taste, but we'll see. So I'll jump straight into it without going to a break. Apologies for that. Okay, the next class of methods are deterministic refinement methods. Coming back to, you know, looking at the formulation of the problem again. Now, instead of 1 dimension, we look at 2 dimensions. And you might say, hey, why is it still in the plane they're talking about? Well, 2 dimensions means that the x vector has 2 numbers. So in particular, it has the slope and the intercept of the line. Intercept the line here, slope of the line defines the inclination of the line. So there are 2 parameters because we're not forcing the offset to be 0 here like before. Therefore, it's a 2-dimensional problem. Our data therefore becomes sort of 3 dimensions, but one of the dependent variable is set to 1. Okay, this is standard treatment, nothing surprising here, so I'm not going to spend a lot of time talking about this. The consensus formulation tries to find a line where as many of the points have distance of no more than epsilon to the line. Okay, find a slab of thickness epsilon that encloses the most number of points. Again, why am I spending time talking about this? Because the next page might throw you off if I don't talk about this. The next page looks at a different point of view of the problem, where instead of showing you the data space, I show you the parameter space, x1, x2, slope and intercept space. Okay, in the slope and intercept space, in the parameter space, every data point, now you have to remember in this space, the variables, well, okay, as before, the variables are the x, but now I'm fixing AI and BI, still the same as before, but I'm checking the space for a particular point. For a particular point AI, BI, I'm checking the subset of the space that enables the line to be within subset, to be within residual epsilon to that particular point AI, BI. Okay, so every point gives you a strip. The strip has different widths because it depends on the inclination of the line, because, you know, indirectly, in fact, you know, as a direct consequence, not indirectly, this is the effect of choosing a special variable, dependent variable. Consensus maximization becomes finding the region where as many of the strips are intersected as possible. So if I scale up the number of points, this is what happens to the surface of the problem. Okay. This is the result of considering, you know, I don't know, 100 points, 200 points. In 2-dimensional case, of course, I can plot, no problem. I'm showing you now. But the color of the regions here tell you the consensus. The lighter it is, the higher the consensus. If I choose x1, x2 here in particular, this allows me that consensus with that particular data instance, okay? And there are others here of the same consensus. And if I plot it in as a 3D plot, surface plot, instead of a contour plot, you get the plot on the right-hand side. What can you say about these plots? Let's start with this one. What can you say about the surface of the objective function? Is it smooth? The ones answering. It's not smooth. And that's because we're counting inliers here. And because of that, you know, it's not smooth. In the one-dimensional case, the equivalent function would look something like that. Okay, it's a step function. All right. In normal optimization textbook, we look at smooth functions like that. The reason I want to highlight this is the consensus problem is piecewise constant. Okay, there is no gradient. Doesn't matter where you look at, there is no gradient. The gradient is 0, except at the discontinuity here where the gradient is infinite. Okay, that's the first point. That's what you get when you spend a lot of time looking at fundamental problems, fundamental nature of problems. You try to pick out, you start to pick out these probably, you know, excessively fussy points. The point to make here, second point, is that for a point in an optimization problem to be considered a locally optimal solution, you have to say that all other points, there is a neighborhood within the locally optimal point where the other points are smaller than, other points' objective value is smaller than it, smaller or equal. Okay, so this would be a local optima. That's cool, that's fine. But for our problem here, with that definition, every point is a local optima, all of them. Okay, these are all local optima by strict definition, by the textbook definition of local optimality. These are all local optima. If these are all local optima, then I can give you any solution. I can give you any of the points here and say, I have found a locally optimal solution to RANSAC. Okay, so local optimality is, in my opinion, meaningless in the context of inlier counting kind of objective function. All right, the textbook definition says all solutions are local minima. We move into, therefore, the refinement problem. The notion of following the gradient so that you get to some kind of stationary point is meaningless. All right, as I've just illustrated. We need to define this refinement problem differently. And here's our definition of it, not the only one, there are probably others. Our definition says, given a current solution x tilde, find a better solution x hat. That's it. Okay? There is nothing to say that x hat has to be in some local region of x. Because, you know, if the local region is what I'm interested in, then the next step I can only move to is that. Not really, but you get what I mean. I can't use the gradient to drive x tilde to a higher value. Okay? The domain that x hat lies in could be non-convex. Okay? So again, not necessarily in the local region. Okay, so what can we do with this? Well, you're gonna jump straight to the method. Here's an alternative formulation using what's called the complementarity constraints. We introduce slack variables as before. We introduce again indicator variables. This time the indicate, yeah, okay, same as before. Indicators indicate which point is an outlier and all that. The model is here. We sum over the indicators and minimize. We want to minimize the number of outliers. And the complementarity comes in these two constraints here. This one is the usual, you know, points must have residuals less than or equals to epsilon. The epsilon is absorbed in the constants beta. The Sj is the slack as before. The complementarity constraints are an interesting one. The second one here says both of these slacks and the indicator variables must be non-negative, and 1 minus uj must be 0 to indicate that uj must be either 0 or 1. It will be forced to be 0 or 1. If Sj is non-zero, that means Sj, the jth point, is an outlier, then I must set uj equals to 1. Okay, I must set it equals to 1 because the right-hand side says the whole thing must equate to 0. So if a point gets a slack, then it must be an outlier. That's all. If this is 0, then that point is not an outlier, it's not designated as an outlier. Therefore, the slack uj must be 0, so that this can be 0. Well, it doesn't have to be 0, sorry, it can still be 1, but then if this right-hand side must be 0 as well. So if this is already set to 1, then this whole thing must be a 0, must be an outlier. Sorry, if this is already set to 1, then this whole thing must be 0. So you have this slack which is as tight as possible for the outlier. If this here is 0, that means that this whole thing can be whatever it wants. The slack, oh, now I don't remember how this works. If it is 0, then Chipeng, can you rescue me? Do you remember how this works?
I think if Sj is 0, then uj can be either 0 or 1. And since we want to minimize the sum of uj, so uj probably
okay, all right.
wants to be 0.
Okay, so uj we want to make it 0 by default. Okay. Okay. In other words, this is implementing that inlier counting thing or outlier counting thing using this complementarity constraint. The interesting thing is when we move this to the objective function, which is here now, and multiply it with a slack. Okay, so that's called a penalty formulation. Instead of forcing that particular constraint, which we've just moved up, to be satisfied all the time, we're penalizing its dissatisfaction. Okay, the strength of that penalization depends on lambda. Why do we want to do this? Well, now you see these are, okay, we don't see that yet, but the benefit of doing that, we'll see later, is that in this page, if we fix lambda and s, so if lambda is fixed, so basically ignore it, we fix s, this is a linear program. If we fix lambda and u, so delete u, delete lambda, this is again a linear program. Okay, and therefore an algorithm for solving this would be to alternate between the two linear programs and progressively penalize the dissatisfaction of that constraint until we converge at some point. And the theory says if lambda is large enough, there is a lambda that is large enough but still finite, the algorithm will converge to a KKT point. Okay, still doesn't tell you how far that KKT point is away from the global optimum and all that. As you know, the theory says if you just solve linear programs, you will never find an algorithm that can do that. Okay, but practically this is how it works. We could start with a RANSAC solution, for example, and then refine it using the two linear program alternation algorithm I've just shown you. Similarly, you know, I could start with this line here, and we've shown that it actually converges quite well. Start with this line here, alternate the two LPs to get to that line. Okay, so which is pretty cool. Okay, some quick notes on evaluation. This is something, so all the algorithms we've mentioned so far, including the ones that were mentioned in the previous segments of the tutorial, set up 8-dimension problems, vary the outlier rate. We record the converged quality and the runtime of the algorithms. And this is on the data that is balanced. You know, why we want to set that up? As you know, there are problems where there are algorithms that become problematic when the data is not balanced. And here is the quality of the solutions. And as usual, you know, CVPR papers, our algorithm converges to the best result. And for our algorithm, we initialize the deterministic one, we initialize using RANSAC or least squares. They both converge well for balanced data. The L1 and L infinity method works well as well. RANSAC, low RANSAC, improved low RANSAC, they all work well. Okay, so within this margin, it's not a big deal.
There's a question.
Yes.
Someone asked, what is the convergence rate of penalty method we just mentioned?
Oh, good question. I don't know. That's a good question. I'm not aware. Sorry. I think we didn't look into it. Sorry. Yeah, but it's a point that's worth looking into. Thank you for that. So in terms of the runtime, as the number of outliers increase, the RANSAC methods predictably go up. Our method that is initialized with RANSAC also runtime goes up, but for the other methods, the runtime is constant for the outlier rate. For the unbalanced data, that's where we see that the outlier removal methods here, they lose out, because as we showed you earlier, when there's unbalanced data, it tends to remove more outliers than it really should. The other methods are still okay. And in terms of runtime, same picture, the RANSAC sampling methods, the runtime goes up when the outlier rate goes up, whereas the others, the runtime are similar. Okay, some experiments on real data. We're not, for this deterministic refinement method, we're not positioning it as a competitor to RANSAC. We're positioning it as a refinement of RANSAC, bearing in mind what we said earlier about local optimality. Okay, for a problem like this, local optimum in the sense of non-convex optimization, where you follow a gradient, you get to a point where all the points around it are either smaller in objective value or has the same, is not meaningful. Okay, so therefore we position our method still as a method that upgrades existing solution, but not a locally optimal. We call it therefore deterministic refinement methods. Okay, so about 10 minutes left to talk about the final segment, which I think is optimal timing. We're starting to look into a different question, all right? There is this fundamental limitation. If you want fast, you can't have guarantees. If you want guarantees, you can't have fast. We can only play with the third line here, which is, we just check whether it's, we just make sure that it's not random. That's what we can play with. But that's if we're restricted by using conventional computers. What if we're not restricted by classical computers? What can we do? Sorry, I have to go through this stuff again, but it is essential to understand the rest of it. This is still the min-max problem that we've looked at before. I'm just attaching, a function called g of c, where I'm allowing myself to consider not only all the points, but a subset of the points called c, that's all, okay? If c is the whole data set D, then this is the original Chebyshev problem we looked at with a quasi-convex residual, all right? I'm generalizing it so that g of c is solving the min-max problem, the Chebyshev problem, but only on the subset c, okay? That's it. And g of c is that minimax value, all right? Let's say here as an example, c is a set of points, the blue points, and g of c is the minimax value, minimize maximum residual of those blue points. Same here, if c are the blue points here, then g of c is that error there. Okay, so again, if this is linear or this is quasi-convex, g of c can be found tractably. Okay, I can just solve using bisection or sequential quadratic programming or a generalized simplex. There are black box methods to solve this globally optimally. Okay, I define a Boolean feasibility test, whereby, well, before I go there, let me define vector z, where z is as long, z has as many elements as I have number of points n, and all the z's are binary, meaning that if I set zi equals to 1, I'm picking that ith point, okay? So Z therefore, lies in 0, n, as I've indicated here, sorry. It's just picking whichever subset I want, okay? So if I give you a Z, that means I'm giving you a selection. I'm giving you a selection of the points. C of Z is simply checking which indices are picked by that Z, that's it, okay? Then I define that Boolean function f of Z. So given a selection indicated by Z, I set the output of the function is 0 if the G of that subset of points, is within the epsilon that we want. Otherwise, I call it infeasible, okay? So this is feasible, this is infeasible. Okay, that's why it's called a Boolean feasibility test, okay? 0 means, again, the points that I give you in Z can be fitted within threshold epsilon. If f is 1, the set of points I give you cannot be fitted within epsilon. That's it, okay? Sorry to repeat on this point. Fz equals to 0 means Z is a consensus set. Fz equals to 1 means Z is not a consensus set. That's it. Okay, so so here's an example of Fz equals to 1. It's not within the epsilon we want. Here's an example where Fz is 0. It is within the epsilon we want. That's it. Okay, so that's a Boolean feasibility test. Now here's the critical concept for this method: influence. The influence of the ith point, alpha I, is the probability that for probability where if I give you any subset Z, that Z may or may not include the ith point already. If it includes the ith point already, I remove the ith point from it. If it doesn't include the ith point in it already, I add the ith point to Z. What I just said there is implemented by this XOR function here. E of I is just a vector of all zeros except at the ith location where it's 1. Okay, so if the Z, whatever those numbers in there are, contain 1 already, if I XOR with 1, the output is 0 in that location. Okay. If the Z contains 0 in the ith location, that means does not include the ith point. If I XOR it, the output will be 1. Okay, so here this is saying again, XOR with EI means if it's already, ith point is already in Z, take it out. If it's not already in Z, add it in. Okay, so the influence checks the probability of, come on, don't crash. Sorry. The PDF reader usually crashes when I do it too aggressively. Don't worry. Not you, I want this. Okay, we're back. So the influence says, for any possible Z, what is the probability that adding or removing the ith point changes the feasibility of the set? Okay, I'm checking non-equality here. Okay, so give you a Z, same Z here, adding or removing the ith point. Has the feasibility of that Z changed? And what is the probability over all possible Z? And because we're considering all possible Z, we're checking, here's a Z where the feasibility changes as a result of adding or removing I. Count the size of that set, divide by the total number of possible instantiations of Z, total number of all possible selections of subsets. Okay, so that's the influence, all right? Again, in words, the influence of a point is the probability of changing the feasibility of a subset Z by inserting or removing the ith datum into or from Z. Whew. How does influence look like? Well, this is a synthetic data. This is the point index. I compute the influence exactly as the equation in the previous page. Yes, this is a small instance with a small dimensionality. I can compute it exactly over all 2 to the n realizations of z, no problem. No problems for me, big problems for my student, but fundamentally it's still possible. Here's the influence of the points, okay? If I threshold here based on the influence, normalize influence, by the way, I can always divide all influences by the biggest value to make the biggest value 1. Okay, if I threshold at this point, these are the ones where the influences are bigger than the threshold, and the inliers, okay, I'm suggesting that already, but these are the ones, they look like inliers, are the ones where the influences are low. Okay, so moral of the story, outliers have high influences, inliers have low influences. We looked at actual problems in computer vision as well, a triangulation problem, so these are all the 2D observations of the same scene point. Some of them are outliers, the ones that are marked in red. And we compute the influence as before, small problem instance, small dimensionality, no problem. I can compute that exactly. Threshold, and these would be outliers. You see that those that are not localized properly are the ones with the high influence, okay? The 3D scene point is here. The inliers all are at the same location. Another example, homography fitting, as long as it's quasi-convex, I can solve, and I've told you that transfer error is quasi-convex. Outliers are, have high influence and inliers have low influence. In fact, this is real data. None of the correspondences here are synthetic, they are real. What this is saying is that real data often is quite extreme in a sense that when an outlier is wrong, it's extremely wrong. When an inlier is correct, it's usually, has very low error. Anyway, the influence idea still works. High influence means more likely to be inlier. Low influence means more likely to be inlier. Okay, so the function f is monotonic. Okay, what that means is that if I have 2 different subsets B of C of the data set D, and B is also a subset of C, the G of B and the G of B is less than G of C, and G of C is in turn less than G of D. Okay, so this is showing here, this is B, this is C, this is D. You can see that the G's grow progressively. Okay, so the influence is in fact related to the Fourier transform of Boolean functions that are monotone, that satisfy this property here. Okay, what we're concerned with in computer vision mostly is how do I compute the influence, all right? With these 3 simple examples, I hope I've convinced you that influence is an interesting thing to do, potentially very useful for doing robust fitting, okay? It gives you a natural characterization of inliers versus outliers. The issue is the computation, all right? Checking 2 to the n combinations is not the way to go. Can we do it do it differently? Well, apparently, yes, you can use a quantum algorithm to solve it. In particular, use a simple quantum circuit called the Bernstein-Vazirani circuit. I'm not going to go through the detail. Very quickly, the data points would be embedded in the function f in a quantum gate called UF in the circuit. And the function f is also implemented here in a quantum gate UF. And the nice thing about UF in our case is that if we're considering quasi-convex residuals only, f can be evaluated in polynomial time. Okay, again, generalized simplex, bisection, sequential quadratic programming, whatever. If it's quasi-convex, then f is tractable. If f is tractable, then there will be a quantum implementation that is also tractable involving a polynomial number of gates. All right. I took that straight out of the textbook. I didn't say that. I'm not a researcher yet in the quantum area, but this is what the textbook says. We start off by initializing the quantum state. Oh, by the way, I need n qubits here and 1 qubit here. Start off by initializing the top n qubits with 0 and the last qubit y with 1. Just bear with me here. There's not enough time to go through the detail anyway. Initialize like this. Apply n+1 Hadamard gates basically put the quantum state in superposition, which looks like that. So now the quantum state, is simultaneously in multiple states. Apply that quantum version of that Boolean function that we're thinking of once, evaluate it once. Apply the n+1 Hadamard gates again to sort of put it back into a less superposed state. And we will see that at the top n qubit, that top n gate here, it looks something like that. Okay, and it can be shown that the weights over all possible S combinations, so this is the same as Z, because I've used Z before, and I've used Z at the start, so I didn't want to use Z at the end. But then this works the same way as a Z, which is to choose the subsets. You can prove that the weights of each so basically the probability for one variable Si to be 1 in the final quantum state is exactly equals to its influence. Okay, so all we need to know at this stage in this tutorial, details can be provided later. In one evaluation of F, we compute all the influences exactly. The classical algorithm will need 2 to the n power times. So that's really cool. Okay, it's a potentially a quantum, an exponential speed up using quantum computer. Unfortunately, limitations by nature allow us to access information by quantum measurements only. So as soon as we measure, the quantum state collapses, and the measurement follows the probability of the influence. The probability, the ith point, if I measure it, gives me the value of 1, is proportional to the influence of that point. So that's cool. That allows us to set up a quantum algorithm that looks like this to compute the influence. Run the algorithm m times. Each time we run the quantum algorithm, we make a measurement. We collect the measurement and collect the statistics to form the approximate influence. Okay, I'm not going to talk about the equivalent classical algorithm. You can do the same classical approximation algorithm as well. The main point is the quantum algorithm has only one outer loop, whereas the classical algorithm has an outer loop where you do m times as well, and an inner loop. Okay, the inner loop is size n. Size n inner loop does not exist in the quantum algorithm, so the quantum algorithm is n times faster. I'm aware that I'm 2 minutes over time. We're almost done. You can analyze the quantum algorithm as well, and you can show that if you run it m times, the probability of the approximate influence that you get is within value delta from the true influence grows exponentially with m. Okay, so the result on the right-hand side here, on the x-axis, it's the number of iterations. The green is the probabilistic bound. The pink is the approximate influence that you get, and you can show that it's within the probabilistic bound. So that's cool. Yeah, so this is satisfied in all the simple instances we looked at. So we looked at a bigger instance. Yeah, sure. I mean, I'm not claiming I have a quantum computer already, but we're simulating the quantum circuit in a conventional computer. We can look at the speed up theoretically. For this problem instance, there are exactly 516 correspondences, and therefore the quantum speed up is 516 times, all right? The theorists will say, oh, this is nothing. I want to see exponential speed up before I call this a breakthrough. But for us practitioners, for us engineers, if you have 1,000 correspondences and you want to compute the influence way to do robust fitting, the quantum circuit allows us the 1,000 times speed up. So that's, in my opinion, amazing. And the approximate influences still work well. This is actually the approximate influences. There's no way I can run the exact, I can compute the exact influences. No way my student would run the exact method, because you need to check all 2 to the n. 2 to the 556 is probably more than a number of atoms in the universe. Yeah, so yeah, there's no way anyone can run this. So we can only get this result using the approximate algorithm. With only about 800 iterations, you can see that the influence is already very useful in separating inliers and outliers. Okay, so watch this space. This is this should appear on arXiv soon in a few hours. So hopefully there'll be more work here. So that's it. List of references. I'm sure I haven't covered everyone. There's great work coming out from teams around the world. So I hope I've listed everyone here on this fascinating topic, in my opinion. Thank you very much. Happy to take other questions if you have any. Marlin asks, do you think there is a way to design fast global algorithms such as bundle adjustment? What do you mean by global? Globally optimal, or global as in it considers multiple viewpoints? Can you clarify what you mean by global?
Yes, I mean it's the global optimum of the solution.
No.
So basically where you have the minimum cost.
At the absolute minimum cost, there is no way. The theory forbids it.
Mm-hmm. So it's pretty pessimistic.
Yes. Unfortunately. But
okay, yeah.
Life hums along. Don't worry about negative results. Negative results are all over the place. Most computational problems, in fact, are NP hard, but you know, life goes on. It's just that as researchers, we need to be careful in what we claim in the paper, that's all. And when we say global, what do we mean global? How do we prove that it's global? We can still have,
all right, thanks.
Yeah, we can still have self-driving cars, no problem. By bundle adjustment, I'm also referring to the original formulation, the L2 error. The L2 error is non-convex. If you sum a bunch of non-convex functions, it's still non-convex. There are probably non-standard bundle adjustment formulations where it's convex, then or quasi-convex. Then yes, it's possible to have global in polynomial time. I'm still happy to take questions, but I'm going to stop recording now.